Good afternoon. Thank you very much for joining us. Today we have the presentation meeting of PhD defense by Mr. MYO ZIN AUNG. This is this opportunity. He will make his research outcome towards a PhD at Osaka University. So after his 40-minute presentation, I will invite a discussion on this subject. So, Mr. MYO ZIN AUNG, are you ready to start the presentation?
Yes, I'm ready, Sensei.
Okay, so please go ahead.
Hello, everyone. My name is MYO ZIN AUNG, and I'm from Ship Intelligentization Sub-Area. The title of my PhD thesis is Simulation Study on Shift Maneuvering Control for Establishing Minimum Propulsion Power Requirement under Adverse Weather Conditions. My PhD thesis includes 6 chapters as shown here. First, introduction. Climate change is now threatening people with a lot of problems, and one of the major causes of the climate change is due to the emission of the greenhouse gases. According to the IMO GHG study 2020, in 2018, the total shipping contributed about 1,056 million tons of CO2 globally, which is about 3% of the total CO2 emission. So to reduce the greenhouse gas and to encourage the efficient ship design, in 2011, IMO mandated the EEDI regulation. And the phase 1 starts from the January 2013, and the regulation will be gradually tightened phase by phase every 5 years. EEDI means energy efficiency design index is defined like this: impact to environment divided by benefit to the society. In other words, CO2 emission by 12 Therefore, the lower EEDI value means more energy efficiency. So this is a little more detailed EEDI formula. So this shows several EEDI reduction measures, which include the design speed reduction, optimization, propeller optimization, engine optimization, energy saving device, alternative fuel, energy carrier, and other green technology, etc. Among these EEDI reduction measures, design speed or the power reduction is the easiest in the expense way, because EEDI is proportional to the engine power, and engine power is approximately proportional to the joule of the shift speed. So by reducing the design shift speed, the power is significantly reduced and EEDI value will be significantly reduced. But on the other hand, small propulsion power can impose the operational danger under the adverse weather condition. Therefore, IMO also included the minimum power guideline in the EEDI regulation. This shows the maneuvering accident caused in the adverse weather condition. The accident occurred before the EEDI requirement, but after if the ship designer decided to reduce the propulsion power, this kind of accident are more likely to occur. This video shows some of the adverse weather encounter in the sea. Now I will explain about the minimum power guideline. In 2013, at the MEPC meeting, IMO adopted the interim minimum power guideline. So up to now, there are a couple of amendments to the initial interim guideline, and a major revision is still in progress. So to improve the guideline, the EU project SHOPRA in the Just Now project contributed the discussion at the MEPC meeting with their research finding. Better numerical prediction model with the precise modeling of wave drift force, wind force, and maneuvering force were also developed. Various analysis and assessment methods were also proposed. The proposed methods are based on the steady-state equilibrium calculation, which are more suitable for the direct application in the regulation. However, the behavior of the ship in the adverse weather condition is more intuitively observable in the time domain simulation. Also, moreover, the ship and trajectory could significantly differ depending on the initial condition, like forward speed and heading, etc. although the final steady state condition may be the same. Therefore, the maneuvering simulation in wind and wave become important. Now in chapter 2, maneuvering model. So for the maneuvering model, the modular modeling approach is used. Here the sheet is divided into the different systems: hard reaction forces, steering system, propulsion system, as well as in the environment, the wind and wave force are considered. Because this is the modular modeling approach, each of the system can be updated and replaced if more accurate method become available. At the same time, I also included the engine in the shift navigation control system, and which will enable the wide range of maneuvering simulation scenario. This shows the 4DOF MSR Royal MMG equation, which is used for the maneuvering model. Now I will explain the force and moment component on the right hand side. For the hard force and moment, the unified mathematical model for ocean and harbor maneuvering proposed by the Professor Yoshimura is shown here. This model can deal with the very large drift force angle in the very low speed maneuvering, which may encounter in the severe sea condition. The correction factor for the cross product coefficient used in this model was obtained from the captive model experiment. This shows the arrangement of the propulsion system, and the propeller. From the propeller module, it will generate the thrust shown here, and the propeller is connected to the engine via a shaft, and the engine is controlled by the governor here. The operator will specify the desired RPM here. The governor also included the fuel limiter, which will ensure the engine operating point is within the specified limit. The shaft dynamics equation is shown here. For propeller thrust in propeller torque is calculated from the open water propeller chart as shown here. For the engine torque, it is shown that the engine torque is proportional to the amount of fuel supplied into the engine, and so here the proportional coefficient can be calculated from the specified MCR point as shown here. For the friction coefficient, it is shown and is negligible. For the engine speed control, PI governor was used. The equation of the PI governor is shown here. So the governor also includes the fuel limiter, which will ensure the engine operating point is only within this engine load diagram. This is shown in the green color here. So in this diagram, the line 1 specifying the maximum speed limit, line 2 specifying the maximum power limit, and line 3 specifying the maximum torque limit, and line 4 specifying the maximum torque speed limit. So the line 4 is mainly due to the thermal limitation of the engine, and this will be the most important one for the simulation in the advanced weather condition. A steering system is arranged like here, and the propeller module will calculate the radar module will calculate the radar force and moment, and the steering gear ensure the maximum radar angle in the radar turning rate, and the radar command is obtained from the autopilot here, and the operator will specify the desired heading to the autopilot here. And the radar force and moment are calculated using this equation from the standard MMG method. Yeah. For the autopilot, the PID type autopilot is used as shown here. For the environmental force, first view force number is defined here, and their corresponding wave height and wind speed are given in this table. In the environmental force, wind force and wave force are considered here. For the wave forces, there are two forces here. The first one is the second order wave drift force, and second order wave drift force, and the second one is the first order wave force, which is the oscillatory motion. For the wave spectrum, Johnson spectrum is used. For the wave PDA, wave PDA chosen at the maximum wave drift force around the healthy condition. This shows the Johnson spectrum here. For the directional spectrum, cosine square function is used here. Wave force are calculated for both long cluster and the short cluster wave here. But when comparing these two forces, the long cluster wave are larger. So for the simulation, long cluster wave force are used. For wind forces in movement, these equations are used. In this equation, the draft coefficient, the wind draft coefficients are estimated as a function of relative shift heading using the Fujikawa empirical formula. For the wave drift forces, they are calculated assuming that they are proportional to the square of the wave height as shown here. This is the wave spectrum. This is the wave drift force in the regular wave, and then they are integrated over all frequency in direction as shown here. The regular wave and drift force are calculated here. For the sound forces, sound wave drift force is MYO theory with Cauchy function calculated by the electric cylinder body. For sway force in movement, I use the linear 3D-dependent method with the Green function for the zero forward speed. For the first order wave, instead of using the first order wave forces, I directly use the first order wave motion because these are the linear forces, and also motion RAO are readily available. Using the wave information in the motion RAO data, and the first order wave motion in CTOF can be calculated using here the superposition of the different contribution of the different wave frequency here. For the proper line remargin, so from the previous here, I can obtain the shift motion of the center of gravity. By using the information, I can obtain the instantaneous proper line in radar position. Moreover, I can obtain the wave elevation at the proper line radar using this equation. By using this information, the amount of proper line radar above the water can be calculated. After that, and the thrust stored in the radar force reduction factor can be obtained. Now, subjects in the validation. The subject in this study is the handy mass bar carrier, and this the half form of this shell is originated from the KVS62, in which is modified to have the block coefficient of 0.84. The engine used for this shell in the propeller are given here. First, validation. First, I will show the validation at the zero speed and propulsion equilibrium, and the validation is only done in the SAS equilibrium. Yeah. So the 4 DOF equation reduced to the here nonlinear 1 DOF SAS equilibrium equation as shown here. In this equation, propeller force is the zero speed bulletproof condition. For the radar forces, so I checked the experimental radar history as shown here. So because there were oscillation in the radar history here, this is due to the unfettered yaw motion in the autopilot feedback in the large differential gain. So because of this oscillation, so I consider the radar force radar thrust will be around 10% of the propeller thrust. Yeah. For the wind forces, this shows the wind draft coefficient, the measured wind draft coefficient in the Fujikawa empirical estimation. Fujikawa empirical estimation is more conservative here. So this shows the result of the 0C Hesse equilibrium RPM for the different weather condition. For wind force and movement, I use the measure parameter in the for wind draft coefficient. I use both Fujikawa in the experimental fit here shown here. It's numerical result with the experimental wind draft coefficient show the good result, and as expected, the Fujikawa coefficient have a little more conservative result here. Now validation for the first order of wave motion. To validate the first order of motion in the irregular sea, I selected one of the previous experiment, but this experiment is not specifically designed for this purpose, but I selected this one to show some validation of the first order wave motion. This is the wave elevation history during the experiment. This is the wave spectrum. This is the trajectory of the ship and during the experiment, and the autopilot heading was specifying 0 degree Hz, but in here, if you can see, the actual heading is not 0 degree. This shows the validation of the heave motion here. It shows the good agreement between the experimental heave motion and the heave motion calculated from the motion IO. Pitch motion also shows the good agreement here. But the roll motion doesn't show the good agreement. This is due to because IO motion are calculated without the advantages, and also during the experiment the radar is oscillating as I have shown previously. So this might be due to this discrepancy is due to the. So now I will show you the maneuvering simulation. First scenario. So the maneuvering simulation scenario is inspired by the grounding accident of the partial barge carrier on the Nobel Beach New Castle Port. Before the experiment, the ship was around the buoyancy condition, and then the shipmaster tried to turn to the Hz to avoid the grounding, but it was unable to turn, and it's finally grounded. Yeah, so in the simulation, the ship will start at the buoyancy, and it will turn to the Hz using autopilot. I executed the 4 different types of comparative simulation. The first one is comparing the between with and without propeller and radar imaging. The second one is the comparison under different weather conditions. The third one, using different initial forward speed. In the fourth simulation, I will compare the different engines. The first one, this is effect of the propeller. This simulation show the with and without propeller in radar imaging. And this diagram shows the propeller in radar imaging history. If the red line is above the blue line, this shows some part of the propeller or radar is above the water. So as you can see here, the propeller imaging doesn't occur very frequently. This is a very long time history, and also the imaging is not very severe. For the radar is a little above the propeller, so this imaging occur more frequently in. So this is reflected in the trajectory here, shift trajectory here. But if you can see the shift speed, and the shift speed is not too much different because the propeller imaging is not severe, but only the trajectory has the difference. Yeah, there were RPM jam, and when the propeller imagines occur. And at the same time, the engine, the governor, the speed controller reduce the fuel interposition to eliminate this speed jam. And this although there's a speed jam, and this is within the limitation. So there's no over speeding. This is the second simulation. This shows the comparison of simulation under the different Buford conditions. Up to the Buford 9, the ships were able to turn to the Hz without any problem. In the Buford 10, and there were significant drifting here. In the Buford 11, the ship was unable to turn to the Hz. If you see the ship speed graph here at the Buford 10, even though it was able to turn to the Hz, the speed is nearly 0. In the Buford 11 condition, regardless of the maximum radar effort, the ship was unable to turn. If you see the engine power develop graph here, in the Buford 10 and 11, the engine power develop is smaller than other weather condition because in this condition the loading on the propeller is very high, and also the engine limit at this propeller RPM are lower, so the fuel limit is lower than other conditions. This shows the effect of initial forward speed in the time domain simulation. So in this simulation, I started with the different initial forward speed and did the various simulation. In this condition, it showed that depending on the initial forward speed, the shift trajectory are significantly different. But if you compare the shift forward speed at the final condition, they are exactly the same. So if the ship is operating in the residual water, this might have the significant impact. So in the steady state calculation, this won't show this kind of results. So another one is the force simulation. For the force simulation, I compare the 4 different engines with 3 additional engines shown here. And the first one is the original engine, which is optimized for the original design speed. It has the 5% light running margin. It is shown blue dot here. What is the light running margin? Light running margin is the light reserve engine power for the heavy loading condition. And this is the light running propeller car. The original engine is choosing like the 5% from the light running propeller car. And then the second engine is has the highest power within this layout diagram. This dotted line shows the layout diagram. When the base engine model is selected, the layout diagram is fixed in. You can choose any MCR point within this layout diagram. For the second engine, I choose the highest MCR point here. The third engine has the lower engine power, 20% lower than the original engine. And I choose this engine because of the EDM regulation, a designer may decide to reduce the propulsion power. The 4 engine is the highest. 4 engine has the higher light running margin, and it has the same power as the original engine. Yeah, this is the 4th engine. It has the maximum distance from the light running margin as shown here. This table shows the comparison of the EDI value in the light running margin for the 4 different engines. The lower engine has the smallest EDI value as shown here, and the higher engine power has the higher EDI value as shown here. The 4 engine has a little larger EDI value than the original engine because they have the same power, but because of the higher light running margin, it has the higher specific fuel oil consumption. If you compare the light running margin, this one has the highest one. Yeah. So this is the simulation result. Yeah, using different engine here. This is the simulation. The blue line shows the simulation with the original engine, and this one shows the higher power engine. It has the a little better trajectory here. The lower engine cannot maneuver the ship to the head sea as shown here. This engine, the light running with the highest light running margin, it shows the best and safest trajectory here. This engine and the original engine has the same engine power. Because of the higher light running margin, this shows the safer result here. Yeah, this shows the time series of if you check the shift speed, the engine, the ship with the engine with the higher light running margin has the higher speed among all the engine as shown here. And also for that engine, the RPM can reach up to the specified RPM, and there's not too much. The engine operating point is within the limit of the time. Yeah, for the other cases like the original engine in the higher engine power, because of the lower the engine envelope, lower engine limitation, it cannot use its full power. here, shown here. Sorry. So this is the conclusion for the maneuvering simulation. The modular simulation model for maneuvering control adverse weather condition is developed, and also the effects of propeller and radar images are considered. So the proposed model is also flexible in changing physical component in the environmental condition. Various maneuvering simulations are executed with the different physical parameters in the environment condition. 4 different simulations are done. When comparing the effects of propeller imaging, the shift speed is not significantly affected by the imaging because the images are not very frequent, but there's some difference in the trajectory because of the radar imaging. Engine overspeeding doesn't occur because the Ph.D. governor was fast enough to compensate the sudden engine speed jump. Engine speeding is more likely to occur in the beam and bound quadratic wave, because in the heavy wave, the propeller RPM is already low because of the heavy loading, so the overspeeding is less likely. All these simulations are done under the ideal condition with the simplified model. So, I cannot take account all the possible effects, especially the engine and dynamic and something, etc. So, in the real situation, there may be some differences. For the different weather conditions, the ships were able to turn to the hazy up to the before turn condition, but with a very fine small speed. In this situation, the radar in the real situation, the radar is angle will be controlled by the human with the discrete form, and the exact wind in which direction are not easily accessible. In this case, and the human control will be less efficient. When comparing the different initial conditions, even though the final steady state are safe, and the ship trajectory are significantly different. So if I use the different initial heading, the ship trajectory also will be more or less significantly different. Therefore, when assessing the safety of the ship in advanced weather condition, not only the equilibrium ship speed, but also the ship trajectory are important, especially when the ship is operating in the residential area. When comparing the different engine or SMCR point, the higher LRM, the engine with the higher LRM gives the substantial advantages over the ship speed and safety, but there will be compromise in the ship speed as well as fuel oil consumption in the AEDI value. Now the second part. In the second part, I studied the ship automatic control strategy. In the advanced weather condition, the ship is usually controlled by the manually, but the manual control is not very precise. So in some cases, the automatic control will be less. Automatic control will be more efficient. In this study, I studied 3 different control strategy, like first heading autopilot alone, and then path following guiding, and then optimal path planning. First, autopilot alone. This shows the setup of the autopilot control alone. So the autopilot will calculate the radar angle for the ship in the orbiter will specify the desired heading. This shows the simulation result of the autopilot alone for the course keeping maneuver here. So under the different weather conditions. So starting from the before 9, the ship shows some drifting, and the before that, the drifting is very large here. This shows the simulation result in the before turn condition for the course keeping of the different oblique angle here. So it shows significant drifting in this before turn condition. So now to eliminate this significant drifting, I added another layer guidance system over the autopilot. The guidance system will calculate the reference heading for the autopilot by using the waypoint in the path sheet and the safe path, straight line path specified by the operator, and the feedback to the guidance system is the shift current position, which can be measured by the GPS sensor, etc. So this is the design, and this shows the design of the LOS guiding. LOS mean line of sight. So let's say we have the two waypoint in the straight line connector here. So we want the sheet on this line, but here there is the cross track error. The sheet is not on the line. And so in the line of sight guidance calculate the desired heading, and by combining these two angles, this angle here and this angle here. So this angle is calculated based on the cross track error here from the line in the look ahead distance specified by the operator here. This look ahead distance will serve as the tuning parameter for the guidance system. So depending on this distance, the ship will move to the path aggressively, or it will move to the slowly. So this shows the comparison of PhD only and then LOS plus PhD here. So in case of PhD only, they were drifting. In case when LOS guidance system is added, and the ship can go to onto the path as shown here. If you compare the radar angle between the PhD only and LOS PhD, the radar angle is not too much different, although the ship trajectory has the significant difference. This shows the LOS PhD simulation, path following simulation for the other angle, other course angle. For the before 9, the ships were able to follow the path for all heading angle. This shows the path following for the before 10 condition. In the PhD only, there were significant drifting. In case of LOS PD, the ship was able to follow the path. In the ship, and the ship's heading is nearly 0. In case of LOS PD, in the radar angle is also 0. This means that it's using the drift forces to keep onto the path. This shows the path following simulation for the before 10 for different paths. The ship was able to follow the path up to the 25-degree path. Beyond that, the ships were unable to follow the path regardless of the maximum radar angle. Up to this point, the collision-free safe path is specified by the user to the guidance system. So now in this session, I added the path planner, which will calculate the collision-free path for the guidance system. The operator only have to specify the initial and final position and then obstacle on the path. For the path planner, I am using the optimal control because in the advanced weather condition, the feasibility of the path and the efficiency of that path is very important. So that's why I'm using the optimal control. The optimal control is designed like this here. There is a course function to be minimized. In my case, the course function is the minimum time. The course function will be the minimum time path planning, and the ship will be subjected to the different constraints here. The first one is the dynamic constraint that will ensure the generated path is feasible for the ship. And then there will be constraint. First, the main constraint will be the obstacle. For this study, I was using the cycle obstacle of 1 kilometer diameter that will be placed on the path about 2.5 kilometers from the initial ship position. This is the optimal control problem parameter in the optimization parameter shown here. Because the generated path from the optimal path planner is the curved path, the LOS guidance is modified to be able to follow the curved path as shown here. This shows the result of the generated path in the path following and the before 9 condition. The blue dashed line shows the generated collision-free path here, and the red is the ship that follow the path. In the before 9 condition, the ship was successfully able to follow the path. shown here. If you check the radar angle, the radar angles are, even though the ship is avoiding the very large obstacle, the radar angles are very small because the generator part is the optimal and efficient part. This shows the 45-degree in course path for here. In this angle, the ships were also able to successfully follow the generator path here. This shows the simulation result in the before-done condition. In the before-done condition, because of the severe wind and wave forces, the guided system was struggling. As you can see here, there were some oscillation in the heading angles generated by the guiding system. Also, there were some deviation along the path as shown here. This shows the result for the 45-degree course in the before-done condition. It also shows some deviation along the path here. So this is the conclusion for this session. The performance of the different control strategy are studied by using the numerical simulation with the 3DOF SASUI MMG model. In case of autopilot alone, the conventional PhD autopilot has the large drifting problem in the high viewful number because its function is just to control the heading regardless of the ship position in the drifting. By adding the LOS guiding as another layer over the PhD autopilot, the ships were able to advance onto the desired path using the compensated reference heading angle aboard the autopilot. During the simulation, Hasi-Go path is found to be the least dangerous in the bad weather condition compared to the other heading, because in the other oblique heading, in the Hasi course, the sway forces in the yaw moment are minimal on the ship. When comparing the PhD in the LOS PhD path follower, there's no significant difference in the radar command, although the ship trajectory are significantly disparate. So this means the difference in the small difference in the radar angle can give the significant difference in the ship trajectory in the severe condition. So for the optimal path planner, I propose the collision avoiding path planner using the trajectory optimization in the direct optimal control. In the for the simulation result in the Buford 9, the guidance system was no problem following the generic path for the all direction. But in Buford 10, the ship will become somewhat course unstable, and the guidance system was unable to follow. The guidance system was struggling to follow the path, and there were some significant deviation. For the larger oblique heading, in some cases, the ship was unable to follow the path regardless of the maximum radar angle because of the uncontrollable drifting. So when comparing the PhD autopilot in the path following cases and also the optimal path planner, the early small and precise radar movement were found to be useful when avoiding the obstacle under the very large external load. If this radar is manually controlled, the human operator cannot control with that precision. So in that case, the automatic control might be more efficient than manual control. This is all of my presentation. Thank you.
Thank you very much. So now I would like to invite the discussion from the allocated examiners. Firstly, Professor Toda, could you make some comment or suggestion for this presentation?
Okay, thank you very much for your good presentations. So you are doing the course study for the maneuvering and usual sea-keeping computation for the wave effect.
Yes.
And you got the drifting force.
Yes.
So at that time, you are doing the propeller emergency effect.
Yeah.
So that emergence effect is a time scale, is a sea-keeping time scale. And you are maneuvering time scale. How did you put that one into your computations?
In the maneuvering, CKIP, I will show you. I use this equation to obtain the propeller and radar imaging.
Yeah.
In this equation, this time for all simulation, I use the time scale, very small time scale, and the time step is 0.001 second. So I think that time scale can manage both CKP in the maneuvering motion.
Okay, thank you very much. And this one, for me, it's a very strange. Your field index is lower. The average is lower in the if you have the emergence. So it means thrust and torque are reduced, but the one blade will hit the surface and one blade will accompany the water. So sometimes the torque is changing. So if you need include those very short time effect for the J d omega dt, I think your engine is different. Shows a different phenomena. So I'm not sure your engine is all right, but for many kind of engines, allowance for the load fluctuation is different. So the air draw effect and the blade hit the surface, those effect is very large. So how do you think about that?
So for this study, I use the simplified engine model. So the RPM jump are coming from only from this only from this equation. So the propeller, when imagine occur, the propeller torque will be lower suddenly, and then it will affect this rate of RPM, and the RPM is spike. So, but I did not consider like the air in pressure, temperature inside the engine cylinder. So in that case, I should use the more sophisticated engine model. In this study, I'm only using the simplified engine model.
You are doing very good. Okay, thank you very much. But I think you should include some air drawing effect or something for the radar and propeller, both radar and propeller. Okay, thank you very much. Okay, I finished.
Thank you, Professor. Thank you, Professor Toda. So next, I want to invite Professor Atsuo Maki.
Thank you very much for inviting me. Very nice presentation, I think. So I would like to recheck the some about the RAO in the sea keeping stage. You showed the you showed the pitch and heave motion were nice. But roll motion was not so good. So then I missed here the reason of the discrepancy. So I think there is some non-linearity or something. But don't you think so? Or you say that? Well, yeah, could you explain?
Yeah. I think the reason is not just one. There might be several reasons. The first one is IO motion are calculated for the bare hard condition. So and there's no radar moving behind the ship. So in case of experiment, the radar is oscillating. As I show here, the radar movement could affect the roll angle. That is one reason. Another reason is there might be nonlinear effect in the roll motion.
So yeah, I would like to say there are a lot of nonlinearity, but damping is one of the reason, I think. Maybe you can include the effect of the nonlinear damping component in the linear form, for example. So you can manage the you can manually change the, for example, damping coefficient or something. Is there a lot of ways? So maybe this is a good thing to enhance your results. これ時間あんまり喋ってたらダメなんですよ。すみません。何分ぐらいありましたっけ？すみません。So
please go ahead.
Sorry. Thank you very much. Okay, so this is one of the one questions. The other question is, could you show me the page 25 and 26?
Okay, this one.
Yeah. So you kindly show the discrepancy between the Fujiwara's method and the experimentally obtained wind drag coefficient. So, how did you experimentally get to the wind drag coefficient, CX wind?
This experiment is done in I think around 2014 by Professor Umeda Sensei, and using the dynamometer and the wind blower.
Okay. Yeah. So yeah, I imagine that this wind drag coefficient is coming from some free learning model data.
Not free learning data.
Okay. Just coming from the captive model.
Yeah, captive fish text. Yes.
His understanding is right.
You're right. That's
okay.
Right.
Perfect. Thank you very much. Okay. So, there are huge discrepancy between the Fujiwara's methodology and actually measured ones. So, how did you fill this gap practically?
So when comparing the experiment and the simulation result, when I use the experiment drag coefficient, so the results show good agreement here. But Fujiwara is, because the coefficient is higher, it shows the conservative result. In case of safety study, conservative result is good, so there will be no problem. But the Fujiwara empirical formula should be improved.
So yeah, maybe Fujiwara's regression formula is was obtained from the I don't know the exact number of the ships, but 20 ships or something. But the ship hull form I used here. Used at that research was maybe not so new. I mean, some old shape of the vessel. So maybe that's what the database should be updated. Maybe. Yeah, this is a nice outcome, I think. Thank you very much.
Thank you very much. So now I invite other discussion from the participants. Please feel free to make any comment or questions.
If there is nothing, I would like to ask one thing about the wind moment. wind force and moment. Why? いいですか？でももしなければですけど。
Just I wanna wait another response.
Yeah. Okay.
Someone will make some comment. We have many almost expert on the control, ship control. Dimas, you want to make some comments?
No, sir, not in
No, sir.
particular. Thank you very much.
You know that this content very well. If not, I want to invite Mark Sensei.
I changed the mind. I would like to ask you first, say, control part.
Oh, control,
Yeah, alternative to Dimas-san, I would like to ask one thing. San, you are introduced to use the collocation method. Maybe, yeah, you did not, let's say, compare the collocation method and the direct shooting method. Yeah, as you know, so there are two methodology. One is the direct shooting and one is the direct collocations. Yeah, I love the let's say direct shooting, but recently I changed my mind. I love now collocation method because let's say recently the let's say optimizer becomes very nicer. And then, what to say, they accept a lot of number of the variable to be optimized. So then, collocation method does not recently, let's say, strength of the optimization ability of the collocation method becomes nicer. So then, can you, let's say, for example, can you say some experience about the collocation method? How, what to say? About the collocation method. Yeah.
I did some comparison between the shooting and the collocation method. The problem with the shooting method is using the embedding the ODE, ordinary differential equation, in the optimization. So to satisfy that ODE, if the ODE use the very small time step to specify the boundary constraint, it's very difficult to satisfy the boundary constraint in the shooting method. In case of collocation method, all the point are collocation point. So in those points, at those points, it's more easier to satisfy the collocation constraint, this dynamic constraint especially. So this means it converts to faster in the optimization. So if I use the shooting method with a very coarse time step, like for ODE solver, very large time step, it might be faster, but collocation results are generally superior when comparing the results.
One of the problem is how to set the time steps. So time step is of course in order to let's say rigorously satisfy the constraint about the differential equation, we needed to choose a sufficiently small time step. But how did you, for example, in this program, this is a ship size, actual ship size calculation. So how did you set the time steps? Maybe this is what Dimas-san want to ask. Maybe.
Yeah, this is in collocation method. Here the time steps are very large because the mesh size is only 20 to 200. So the whole trajectory is divided into the only 200 part. So here this is the trajectory. The trajectory only divided into the 200 part. This means the mesh size are very large. But because when generating the part, we don't need very precise how to say precise constraint maneuvering ship constraint, because when following that part we have the feedback control. So feedback control can eliminate that problem. The generator part is not very precise part. It's like kind of cost part, but because of the feedback control of the PhD in the LOS guidance, so there's no problem, I think.
Okay. Thank you very much. Yeah, very nice discussion. Thank you very much.
Thank you very much. It's time to conclude this sessions. So this is end of the defense presentation. Thank you very much for kindly attending and making useful discussions. That's all for these discussions. Please make approach. Thank you very much, Mr. Mill. So the other than Professor Toda and Professor Maki, other people please leave these sessions.